Section 6.2 extends our discussion of rational numbers to include combining them. And specifically what we're going to do to combine them is we're going to start with addition and subtraction. So to start with, addition of rational numbers is going to be broken down into kind of two components. The first one is addition of rational numbers that have like denominators that match. And then the second definition on here has the unlike. So we see like right here and we see unlike right here. So when we have like denominators, like we have a over b and c over b, all we need to do is we need to add the numerators together. And I'm sorry, I don't remember your name, but you had mentioned drawing pictures earlier. Pictures are a great way to justify for kids why this works. So for instance, if I had 1 over 5 and I have 2 over 5, for instance, and want to add them together, a wonderful way to do that would be to draw a picture. And so I'm going to draw a circle. And in theory, I'm going to split it into 5 equal pieces. They aren't going to be equal, but just, for the sake of argument, pretend like my picture looks halfway decent. I know it doesn't. But pretend. And we would have 1/5, so this is 1/5. Right? We ate 1/5 of the piece of pizza or whatever. And then somebody else came along and they ate 2/5. And so you can see that the total is 3/5. The tendency is for students to sort of do the addition across the top just fine. That's 3. But the addition across the bottom, they actually add. So they might write that the answer is 3/10. And so a diagram really justifies why that doesn't work. It really is 3 out of 5 pieces of pizza or whatever justification you're using in terms of a visual diagram. So that's numerators, or that's like denominators. And when you have unlike denominators, there's 2 ways to do that. One would be to get a common denominator. Okay, and that's what this was actually doing. And the other one is to get a least common denominator. So when we have the opportunity to do least common denominator, I'll show you what that looks like just to remind you. This one though, it works in general for anything. It's a common denominator approach. And what you'll see is that same butterfly going on that we had before, right? So here's that a over d, the a and the d, and you see that multiplied right here. And then you have the c and the b, and you see that here. And then the denominator is what gets multiplied together. And if I'd circled it in pink, you can kind of see I've almost got a happy face going on. You see my happy face? That's kind of cool. And so there's a visual to this that's actually also really nice. This isn't how I learned how to do it, but I think for the visual people, this works really, really well because I have a picture of what I'm doing in my mind instead of working with just the numbers that are concretely on the screen. So that's something to think about when you're looking at this. So we're going to do a couple of examples of these next. We're going to take one that's 1/3 and 5/3. So they have a common denominator, which means what am I going to do? Add the tops to get 6. What's my denominator going to be? 3. And when we have the ability to do so, we will reduce. So 6 over 3 would be 2. So we actually get an answer of 2 on this one. If I had done this differently, like 1 over 3 and 4 over 3, and the answer had been 5 over 3, we could have left it that way. Since we weren't told that we had to do anything specifically with mixed numbers or anything like that, that would have been appropriate. Okay? All right, so that's common denominators. This one does not have common denominators. So we're going to practice the visual, I guess you'd say, that we did on the other screen. I'm going to multiply across these diagonals, and I'm going to put my little smiley face in the bottom. All right, so I'm going to multiply the top down on the first diagonal. I'm going to get 1 times 3 is 3, plus 4 times 5 is 20, over, and then I'm going to multiply across the denominators. 4 times 3 is 12. And if I combine this, what do I actually get? 23 over 12. And just like I said on the previous screen, because I wasn't told that this had to be done specifically in mixed number form or anything, then this is a perfectly legitimate way of leaving the answer. Now we would want to look to see if it can be reduced, but 23 is prime, so it's not going to be reduced. But if it could be, we would do that still, even if we didn't change it to mixed number form, right? So having toyed with the word several times, I think we should talk about what mixed numbers are and how those are used. So mixed numbers are used in everyday life to represent values that are an integer combined with a proper fraction. So integer means they can be positive or negative for the sake of what we're talking about here, whole numbers, so like -5 or positive 72, okay? And then proper fractions are fractions where the top is smaller than the bottom. Okay, that's a proper fraction. So for example, these two numbers are the same, 5 over 2 and 2 1/2. But if you were talking about eating a number of cookies and you told somebody, I ate 5 half cookies, or 5 halves of a cookie, it would sound awfully odd. We don't usually talk like that, right? We don't. But if you said, I ate 2 1/2 cookies, that would be quite reasonable. That's how we would speak when we were talking about something in that context. So we use the 2 1/2 in that context because that's how we talk. That's what makes sense. But taking a look then, we're going to talk about how we change numbers back and forth. And I know that you guys have seen this before, but just as a quick reminder, when you're looking at the 14 over 3 and you want to turn it into a mixed number, do you remember what you do?
See how many times 3 is 14.
What's that called? What operation are you using?
Division.
Division. Somebody said it, division. We're just going to divide. So the 3 goes on the outside and the 14 goes underneath. Okay? And this is division like you do in early childhood stuff, right? So this is where we've got remainders and stuff going on, no decimals or anything like that. We're actually looking at how many whole times does it go in and what's left over. Okay? So how many times does 3 go into 14? 4. What is 4 times 3? 12. And if I subtract, I get 2 left over. 2 is smaller than 3, so I know I'm done. So the answer would be 4. That's the quotient on top. The remainder, 2. And then the value that I'm still dividing by is 3. So this is 4 2/3. And that's how you say it, actually. You use the word and between the two pieces, 4 2/3. And again, if I said I had 4 2/3 cookies, that would make sense. If I said I had 14/3 cookies, it's just not how we talk. So, all right, we're going to do the other direction now. We're going to take something that's actually in mixed number form and turn it into an improper fraction. So now I've given plenty of justification why mixed numbers are valuable to us in the fact that that's how we think and speak. So why would we want to turn something into an improper fraction? Well, the reality is it's a lot easier to work with fractions than it is to mix numbers in the middle of an operation. Adding and subtracting, multiplying and dividing is very messy when we work with actual mixed numbers, especially the multiplying and dividing. I'm going to show you how to do addition and subtraction, and it's actually quite clever with mixed numbers, but the multiplication division is messy. So it is often useful to us to change that number, or if we're trying to combine fractions or things, or compare, also quite messy. All right, so what do? Well, the first thing I want you to recognize is that the negative is going to just be there. Okay, so you can ignore the negative for the purpose of what I'm going to do right now, and just recognize in the end our answer is going to be negative. Okay? So we're going to take the 3 and the 5/8 and work with it just by itself. I'm going to show you why this works, but let me show you the visual for how this is so nice and pretty for a lot of students first. So I'm going to draw some circles. Well, not circles, but arrows. There's going to be a multiplication symbol here. You could use a dot if you want, and I'm going to use an addition symbol here. So what does this say? Well, it says that I can take the number 8 and multiply it by 3 to give me 24. And then I can add it, following my arrows, I can add it to the 5. 24 plus 5, 29. So I've got the number 29 over the same denominator as before, 8. Visually, this is wonderful. This gives us sort of a picture image of what to do. So you might kind of be thinking, yeah, that's great, but that sort of looks like a little bit magic-y. You know, like, ooh, that was a cool operation. No idea why it works. Well, it's really quite simple. When you multiply the 3 times the 8, what you're really doing is getting common denominator. This 3 is really 3 over 1, and the 5 is 5 over 8, like this. So when you're multiplying this by 8, you're really doing this. This gives you the 24, and this gives you the 8. And so really, you're just getting a common denominator, and you're adding the 24 plus the 5 together. It's really not magic at all. It's just sort of a shortcut to writing it all down. Cool. Yeah? Am I done? Is the answer 29 over 8? It's negative. Yeah, I told you to ignore it, but don't ignore it in the answer. We do need it in the answer. It is negative 29 over 8. All right. A couple of properties are coming next. This property is the additive inverse property of rationals. For any rational number a over b, there exists a unique rational number, negative a over b, such that when you add a over b plus negative a over b together, you get back 0. So any fraction will work, any whole number will work. So if we take the number 5/3, 5 over 3, its additive inverse would be negative 5 over 3, right? And it works for whole numbers the same, right? So if you have the number 100, its additive inverse is negative 100. And it works if you start with a negative as well. So if you had negative 7 over 6, and its additive inverse would be 7 over 6, or positive 7 over 6, if you want to be clear, yeah. So this is true for every rational number except 1. 0. And 0 sort of works. It just doesn't work in this sort of a form, right? Because we don't usually write 0 over something. But even it in and of itself kind of works because it's its own additive inverse. 0 plus 0 is 0. Okay. All right, it just looks a little different. All right, another property is the additive property of equality. So this additive property of equality says that if you have two fractions that are equal, a over b is equal to c over d, then for any third rational number, e over f, if you add it to those first two numbers, they still stay the same, equal. So I know that feels a little bit awkward and it looks like there's a lot of letters going on, but if you think about what this is it's saying, for instance, if you had 1/2 and 2/4, I mean, they're the same, right? Yeah, they're the same. And if you wanted to add then the number 3 over 7 to it, then if you added 1/2 plus 3/7 and you added 2/4 plus 3/7, they would also be the same thing. Okay? That's all it's saying. And the reason that's nice is because that gives us the ability to write a fraction in a different form and still do all the operations that we wanted to or we're supposed to do with the original fraction. This note on here is something because we're going to see this happen periodically throughout what we're doing is we're going to work some equations. These two properties are really helpful with equations. They're what allow us to actually solve equations where you had teachers probably say something like, if you do it to the left-hand side of the equation, you have to do it to the right. Well, that's actually this property, additive property of equality. Whatever you do to the left, you have to do to the right. So we're going to be using that when we solve equations. And that's exactly what we're doing next. So we're going to solve for x in the following. We want to get x alone. So thinking about what you remember from an Algebra 1 course, probably is where you first saw it. Do you remember what you have to do to get x alone here? Yeah. We need to get that 2.5 on the other side. And so we're going to do it by adding it to both sides. So as we do that, recognize what you're actually using is that additive property of equality, right? That's what allows you to do that. The other thing is that why is it 2.5? Well, it's 2.5 because that's the additive inverse, isn't it? I mean, again, that's what allows you to do that. That's what cancels that out or zeroes that out or something like that. Now, what I'd like to do at this point is I'd like to sort of pause the question because I want to show you that there are two ways to do the problem from here. Okay? And you've probably learned one and not the other, but you may have learned both. The first way to do it, I'll show you, is the way that I learned when I was you guys' age, and that's to do it with improper fractions. This is not my favorite method now. I like the other one better, but this is the one that is prevalent in a lot of math books and ones that probably you've seen. So this is to take each of the numbers, 3 1/3 and 2 1/2, and make them improper fractions to start with. So what would we get if we did 3 1/3 into improper form? 10 over 3. And what would we get for the 2.5? 5 over 2. All right, so now instead of 3 1/3 plus 2 1/2, I have 10 over 3 plus 5 over 2. I need a common denominator, and since 3 and 2 don't have anything in common, it works just as well to make my smiley face, right? So I'll do it that way. So I have 10 times 2 is 20. 5 times 3 is 15. And then in the denominator I have 3 times 2 is 6. 20 plus 15 is 35 over 6. Now here's my question to you. Do you think I get to leave it like this in this particular problem? I get lots of people shaking their head no. Why not? Yeah, you guys remember from last time. It started out as a mixed number. which means the answer also needs to be in a mixed number. So it's sort of awkward because, it started as a mixed number. I turned it into an improper fraction. Now I need to turn it back. You sort of have this sort of a conversion twice in there. How am I going to turn 35 over 6 into a mixed number? You divide. Very good. 35 divided by 6. And you may not actually want to write this part down like in this form, which is cool. But what is 35 divided by 6? It's 5. 5 times 6 is 30 with a remainder of 5. So 35 over 6 is the same as 5 and 5 sixths. Now, if you like that method, that's great. Totally cool with that, okay? But I do want to teach you another method because it is becoming more common to see this used. And for some of your students, it may work better for them to think about this way. So this is a mixed number approach, okay? So we're not going to turn anything into improper fractions at all. We're never going to turn it into an improper fraction, which also means that the answer is more likely to still be in a proper fraction form when I'm done and I don't have to do the division step. So what does this look like? Well, it regroups things. So the first thing I do is I regroup the whole numbers together and the fractions together. And I'm allowed to do that because of a property called commutativity. Numbers are commutative. I have addition with whole numbers, addition with rational numbers is commutative. When I do 3 plus 5, it's the same as 5 plus 3. Okay? It's also associative, so that means that I can rearrange the order of things. Instead of having to do A plus B plus C, I could do A plus C plus B. I can change the order around, so those kinds of things like that, and do the addition in different orders. So why is this nice? Well, this is nice because already I've got the 3 plus the 2, which is 5. Now, I still have fractions that still have denominators that are not the same. But the benefit to what I'm doing here is that the numerators are smaller than they were in the other approach, right? So when I do the multiplication, I'm dealing with a smaller set of multiplication numbers. Now, granted, on this particular one, 2 times 10 and 3 times 5 is not too bad. But sometimes these are ugly. They just aren't friendly. They're very ugly. And so the bigger the numbers you have that you're dealing with, the messier they are. So on this one, though, even with the small numbers here, it's very friendly because I have 1 times 2 is 2, plus 3 times 1 is 3, over 3 times 2 is 6. And lo and behold, I'm actually at the point where I have an answer. I have 5 and 5 sixths. And it's a considerably shorter process. It isn't always. When we get to the subtraction one, you'll see that this particular subtraction one I picked has sort of a different flair to it. But for the addition on this one, it worked really nicely. It was very friendly. Either way, of course, you should get the same answer, right? Yeah. Okay, so let's take a look at subtraction. If A over B and C over B are rational numbers, then A over B minus C over, that should say C over D. There is a typo. Please fix that if it's wrong. Is it wrong in your notes? If your notes are right, it's just my screen that's wrong. Fantastic, that's better. All right, so this should say A over B and C over D are rational numbers. Then A over B minus C over D is the unique value E over F, such that A over B equals C over D plus E over F. This feels really awkward. All that it's saying, and I'm going to use whole numbers to show you just because you can see it very clearly, but it works for rational fractional numbers as well. It's saying that if you did 5 minus 2, the reason that the answer is 3 is because 5 is equal to 2 plus 3. It's sort of what's missing. The subtraction part is what's missing in the second value that wasn't in the first. That's all this definition is telling you, the definition of subtraction. Now, theorem 6.8 down here is also telling you something that you probably know. In fact, I have this very distinct memory in 7th grade of my teacher coming in, it was maybe the first day of 7th grade, saying there's no such thing as subtraction. And we looked at it and we're like, say what? Like, what are you talking about? And what she did is she said it's all just really addition of negatives. Right? Subtraction is addition of a negative. That's all this is saying too. It's saying that when we put the minus sign between it, all it is adding the negative. So it's adding the inverse, the additive inverse of, in this case, C over D. And sometimes that helps students. I know that when I was doing teacher observations for one of my student teachers a couple of semesters ago, I think it was last fall actually, their resources they were using kept using the phrase keep, change, change. And so when she saw something like this, what she would do is she would keep the first number the same. She would change the middle number, or the middle value, which is to an addition sign, and then she would change the sign on the second one as well. So she kept using the phrase keep, change, change, and that was the resources that they were using, the phrasing. And so I thought that was quite clever as well. So they were doing the same thing, but they were using some kind of a mnemonic device for doing that, which was clever. All right, so let's talk about how we actually do this with the like versus unlike denominators. All right, so if we have a over b and c over b, they have the same denominator, and we want to subtract them. We do the same thing like we did with the division, or sorry, with the addition. We subtract the numerators, right? A minus b on top, a minus c on top, and we keep the denominator the same. Okay, so, and again, a visual picture for that is a really good argument of why the denominator doesn't change. All right, so I have 5 out of 6 pieces of pizza, and Susie comes along and eats 2 out of 6 pieces of pizza. I have 3 out of 6 pieces of pizza left, so it's 3/6 left. The addition, these both say addition even. Well, that's what happens when you copy and paste, I guess, right? So this should say subtraction, of course. Your papers do. This is fantastic. Great. Well, I got it right in one place. The place where it matters, I think, probably more, right? All right, so these should say subtraction of rational numbers. If a over b and c over d are then different denominators, then we need a common denominator to do that. And again, one of the ways to do that is to take this sort of a visual approach to it where we're cross-multiplying. That's kind of what it looks like anyway, or at least multiplying along the diagonal, and then multiplying the denominators together. And again, that's not always the best way to do it. That doesn't always, in fact, it usually doesn't give you a least common denominator, but it does give you a common denominator, and you can go from there. So that's one way to do that. All right, so we're going to do an example now of one that's kind of messy. And the reason it's messy is because I'm jumping straight into the mixed numbers, and I put something in here that's got lots of them in here. So this is more complicated than any of the ones you're going to work with. How's that? Don't you always think, man, she did all the easy ones in class and she didn't do any hard. This is a hard one, okay? All right, so let's take a look. Martine brought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8 yards, pants using 2 3/8 yards, and a vest using 1 2/3 yards. How much fabric will be left over? Now, truly what Martine's going to do, if she really does this, is that she's going to lay out all the fabric, right, across the floor or whatever, and she's going to cut off these pieces one at a time. So one way that we can do this is we can take 8 3/4 and subtract the 1 7/8. That's what she would really be doing physically. And then we can subtract the 2 3/8. And then we can subtract the 1 2/3. And that's totally fine. There's nothing wrong with that approach. What other approach might we want to do instead? We could. We could add all the smaller values together of the 3 pieces of clothing she's going to make and then do the subtraction just one time. And I think that's probably a quicker approach to the problem, so how about we try that one? Does that sound okay? All right. So what we're wanting to do, like in terms of an equation, or not an equation, but an expression, is we're going to take the 8 3/4, and we are going to subtract, but we're going to subtract the sum of the 1 7/8 plus the 2 3/8 plus the 1 2/3. Right? This is what you guys told me to do in a written out form. Sound good? Now, 2 of the numbers inside my parentheses are convenient. Why? They both have 8s in it, right? So whether we're doing mixed numbers or improper fractions, we might as well combine those because they're very quickly combinable, right? I don't think that's the actual word, by the way. All right, so we have 8 3/4. And then I've got the 1 and the 2, so this is 3 and what? 10/8, which isn't all that helpful for 2 reasons. Tell me one. Improper is one reason, and the 8 and 3 is not the problem. It's something else. You could reduce it. 10 and 8 are both even, so they can actually be reduced. So the first thing I'd like to do is let's fix the fact that it's reducible. Let's do that one first. So if I have the 10 and the 8 and I reduce it, what will it reduce to? Yeah, 5 over 4 actually. Careful, we get the 5 on top on that one. It is still improper in this form. What is 5 over 4 as a whole number? Or as a mixed number? Yeah, it's actually 1 1/4. So if I have 3 5/4, and 5/4 is 1 1/4, what do I really have? 4 and 1/4. Okay, so no matter whether you like improper fractions or the mixed number approach, this is we do want to combine those two numbers together in some form first. I'm going to keep going with the mixed numbers because I've kind of already started here by accident a little bit. Not accident, but by default here I've started that approach. So we're going to continue with that one on this particular problem. And then I'll show you the mixed number approach with it, or the improper fraction approach with it after that. All right, so if I take a look at the mixed numbers here then, I've got the 4 and the 1, which is a grand total of 5. And then I've got 1/4 and 2/3 that need to be combined. So I'm going to multiply across my diagonals and add the result of that to the 5. So we've got still an 8 3/4 out in front. Now I have my screen. I have 5. And then I've got 3 plus 8 over 12. Does that look right? Okay, awesome. So here's my 8 3/4 minus. 3 plus 8 is 11. So this is, actually I don't even need the parentheses anymore. This is 5 and 11 over 12. All right, so far so good? Okay, I'm going to do the same thing I did with the mixed numbers before. That is, I'm going to work with the fractions and the whole number separately. So 8 minus 5 is 3. The 3/4 and the 11/12 is a really good example where I probably don't. This is a plus sign, and then I'm going to combine these with subtraction. I probably don't want to do the cross multiplication on this one, right? Crossing the diagonals and so forth. Why? Yeah, because if I take a look at those denominators, I can actually turn one of them into the other one pretty easily. So I agree. I like the first denominator, just multiplying it by 3 and going from there. And if I do it to the denominator, of course, I have to do it to the numerator as well. So I've got the 3 in front, and I'm very quickly going to run into a small problem that doesn't happen with addition. What is the problem? Yeah, I've actually got a negative. Now, I can take the negative at the moment, but the reality is I've got 3 minus 2/12. 2/12 can reduce, so let's go ahead and reduce it. What is 2/12? Yeah, it's 1/6. But I do end up having something where I've got, a whole number, 3 minus 1 over 6. Any idea what we would have to do? I think Andrew already said it, actually. We need to borrow, right? We need to take one of the numbers that are in the 3 and we need to borrow from it. So what I'm really going to do, and the word borrow is exactly the right word, is to turn this into a 2. So I'm going to only have 2 left over. And whether I write it or whether I just think it, I've got the whole number 1, but I want to be able to combine it with 1 over 6. So I really have 6 over 6, right? So this is really like breaking the 3 into 2 and 6 over 6. So that I have 6 over 6 minus 1 over 6. Now, those of you who are looking at this and saying, man, I just wish I'd use improper fractions, you run into the same problem. It's just done a little bit differently. So bear with me, you're going to see it there too. But this is going to be 2 and then 5, 6. Units? Yards. Okay, so let's see what happens then if we do improper fractions, okay? So we have the same original problem. It's 8 3/4 minus, and I've got a grand sum total of 1 7/8 plus 2 3/8 plus 1 2/3. Did I get them all in there right? I think so. Okay. I need a common denominator, and I've got denominators right now of 4, 8, and 3.
24.
Yeah, we could do 24. There's one other thing we could do, sort of in hindsight, because we did something just a minute ago, we might realize that when we combined these two, I ended up being able to reduce them, right? So I want to deal with just those two, and I'm going to turn them into improper fractions and everything first. But it'll be reducible, which means I won't have to have quite as large of a denominator to start with, which might be a little bit friendly. 24 as a denominator is quite a large denominator, actually, for what we've been working with compared to the other screen. So let's take a look at this one and see if we can get any kind of a smaller denominator going on. So we're going to turn them all into improper fractions, though, first. So I've got 4 and 8 and 3. So what does that give me? Do you remember? Like this, improper? What's 4 times 8? 32 plus 3? 35. So we've got 35 over 4. 1 7/8. What's that? 15 over 8. 2 3/8. 19 over 8. 1 2/3. 5/3. Okay. 35 fourths. So if I actually turn these into all having a denominator of 24 here, I'm going to be multiplying 35 times 6. It's probably not in your storehouse of things you've memorized as additional facts, right? You just stuck in there multiplication facts. I'm also going to be multiplying the 15 times 3, the 19 times 3, and the 5 times 8. I mean, the numbers are going to get pretty large. So at least combining the two that have the same denominator first seems reasonable. It's less multiplication to do, so we're going to do that first at the very least. So 15 plus 19. 34 over 8, and hopefully at that point you realize and noticing it, oh yeah, those simplify or reduce, right? They reduce because they're both divisible by 2. Oh, I'm sorry. Thank you. Let me fix it. Perfect, thanks. All right, so what's 34 divided by 2? 17, right? Yeah, okay. And 8 divided by 2? 4. And that's very nice because I already had a 4 as a denominator somewhere before, so that's kind of nice. Now I just need a common denominator between 4 and 3, and that's just 12. So I'm at least a little bit happier with that than I was before with the 24 being so big. So I have 17. In fact, you might even want to do the combination of the 17 over 4 first. Whoops, that would be minus. Just because they both have denominators of 4. That's kind of friendly on this particular one. What would be 35 minus 17? 18 over 4 minus 5/3. Now at this point we do have to get a common, we're done. We can't do any more tricks. There are no more tricks up my sleeve. We are going to do some kind of a multiplication of these things actually together to get a common denominator. And I do have to multiply 18 by 3. Oh, we could. I'm sorry, I didn't even see that one. Yeah. Okay, let's do that. What do you want to reduce the 18 to? 9, and then the 4 to... Okay, fantastic. That's even smaller. You guys are seeing all sorts of fun stuff. Okay, I think, though, what I said before is true now, right? No more reducing? Okay, good. Fantastic. Oh, and I like the multiplication better. Do you? All right, good. What's 9 times 3? 27. And then it's minus 2 times 5? 10 over 6. 27 minus 10? 17 over 6. And then we do, in fact, have to do the division, right? Whether it's written or in our head. 6 goes into 17 twice, giving me 12. Then the remainder is 5. So the answer is 2 and 5/6 yards, just like it was before. Any questions on that one? All right.